In this video, we are going to look at more undecidable problems using new techniques. Okay, so the techniques we're going to use are called reductions. Okay, so here's reductions via computation histories. So here's the definition of what an accepting computation history is. It has to do with a Turing machine and an input W. Okay, so we let M be a Turing machine and W an input string. And accepting computation history for M on W is a sequence of configurations, C1, C2, up to CL, where C1 is the start configuration of M on W, and CL is an accepting configuration of M. And each CI legally follows from CI minus 1 according to the rules of M. According to the transition functions of M, a rejecting computation history for M on W is defined similarly, except that the last one, CL, is a rejecting configuration. Okay, so record that a configuration is a snapshot of the current state and the current location of the read-write head. So we often denote it by, say, a configuration CI is U. Let's say current state is Q and V. So this means that on your tape, you have U and you have V, and your Q points to the first symbol of V, and then you have blank afterwards. Okay, so initially, C1 is the initial state and the input string W. Okay, and then CL is a halting configuration, which could be CQA V if it is accepting computation, or CL would be UQR V if it's a rejecting computation. Okay, so a computation history is finite because it halts. Okay, so a DTM, a deterministic Turing machine, has at most one computation history on any input W, while a non-deterministic Turing machine may have several, right? Because we know that a non-deterministic Turing machine is a computation from an initial state, Q0W. It's like a tree. So some of these accept, some of these reject. So we would have a number of computation histories. Okay, so a linear bounded computation is a restricted type of Turing machine wherein the tape head isn't permitted to move off the portion of the tape containing the inputs. So what that means here is that Say you have a tape, and then you have a boundary here, and your head can only move within this range. Okay, if the machine tries to move its head off either end of the input, the head stays where it is. Okay, so this is the left end, this is the right end, so you can, its moving range is only in this part. Okay. So in the same way that the head will not move off the left hand end of an ordinary Turing machine's tape. Despite their memory constraint, linear bounding automata, or LBAs, are quite powerful. For instance, the deciders for A sub DFA, A sub CFG, E sub DFA, and E sub CFG are all LBAs. Every CFL can be decided by an LBA. So it's a linear bounded automata. Coming up with a decidable language that cannot be decided by an LBA takes some work, which is out of the scope of this course. Okay, next, let's look at the LBA acceptance, and which is decidable. So we define the language A sub LBA to be the set of all encodings of a Turing machine M, comma X, where M is an LBA that accepts string X. So first, let's look at this lemma. Let M be an LBA with Q states and G symbols in the tape alphabet. Then there are exactly Q times N times G to the N distinct configurations of M for a tape of length N. Okay, so this is the boundary, and the Turing machine M does not move outside of this range. If it wants to, it will just remain at the end, at one of the ends. Okay, so then how many different configurations we could have? Okay, now remember, G is a symbol. Okay, so that means that in every of this cell, we could be one of these symbols. So then we have n many cells. So you have G to the n many different memories, but then a configuration also has a state, and also it has locations. So you have a Q states and you have n locations. Then of course the total number of different configurations is exactly the number of states times the number of locations times the total number of symbols of length n. So that's G to the n. Okay, so the proof for this lemma is straightforward. Then A sub LBA, then we can show that A sub LBA is decidable. So here's a proof. We construct a Turing machine decider as follows. Okay, so once again, decider means that for any input, it always holds. So that is the first thing. So now on input, M, comma X, this is encoding, with M being a Turing machine, is when being a linear bounded automata or Turing machine with a linear tape run M on input X for Q times N times Gn steps, or before that number of steps if M of X holds. Okay, so you only, so at most this many steps, if before that many steps, this M holds, then the decider holds, okay? But nevertheless, after this many steps, the decider holds. So when it holds, then we'll check. If M accepts X, then accept. If M doesn't accept X after these many steps, which could hold, which could hold at a reject state, or it doesn't hold, then the decider will simply reject it. Okay, so then the decider always holds because we have a bounded memory, so which is the memory tape is linked as a bounded memory, and you only have finitely many. So you only have Q and G to the N, many different configurations. And a computation is a sequence of configurations from one to another following the determined by the transition function of this LBA. So when you run that many steps, if it holds, it holds, okay? If it doesn't, it also holds. And then if M accepts it, accepts the input, D will accept it, otherwise D rejects it. So A sub LBA is decidable. Now again, the most important part here is that we can let a Turing machine, we can compute a decider that always holds within a bounded memory because there are only finitely many configurations depending on the size of that memory, and which is bounded. Okay, so this is the proof. Next, we're going to say that this language on this LBA, and we want to know whether this LBA doesn't accept anything, is undecidable. Okay, so we let E sub LBA be the set of or encoding of LBAs where this LBA, encodings of LBA M, where M doesn't accept anything. Okay, so in order to prove that this is undecidable, it is easier to prove the following language is undecidable, which is just the complement of ELBA. So we are going to, so that non-empty sub LBA, which, sorry, it's LBA, which is just the complement of E sub LBA. So that means that the language accepts something which is not empty. The language accepts by M is not empty. And this is not decidable. Okay, so to prove that this is an undecidable, we will reduce ATM, A sub TM to NE sub LBA. So we're going to reduce A sub TM to NE sub LBA. So remember that A sub tm is the following set of input. So you have an encoding of a Turing machine, M, and a input X to M, where M is a Turing machine accepting X, and M accepts X. So we know that A sub tm is not decidable. Okay, so we prove that A sub tm is not decidable by diagonalization. So now we are going to reduce A sub tm to NE sub LBA. So that means that this reduction will take this as input and produce an output that should be just a LBA. Let's call it M sub L. Okay, so what is M sub L does? Now we need to describe what this M sub L is. So this is the description. Okay, so this is so anything begin after such that is the description of M sub L. So M sub L takes W as input. Okay. So this is my W. And then what we're going to check is to see whether this W is actually an encoding of an accepting, of a encoding of a computation history of M on X. Okay. So then, of course, M sub L will not go off this boundary of W, because what we are doing is simply check whether W is a computation history of M on input X from the initial configuration to a halting configuration. Okay. So of course, we can only have two answers. One answer is no, so it is not a encoding of a computation history. Then we simply reject it. If the answer is no, then we reject it. If the answer is yes, which means it does encode a computation history of M on X, of course, which could either accept it, which could either be accepting or rejecting. So if it's accepting, then we accept. So this ML accepts X. Otherwise rejects. Okay, so thus, okay, M accepts X if and only if M sub L accepts W, which is an encoding of an accepting computation history of MX. And then, of course, we know that ML accepts W. That means that the language accepted by ML is not empty. Hence, this reduction holds. Okay. And we also know that M sub L is an LBA because it remains in the boundary of W. Okay, so that is a reduction proof. So we know that now NE sub LBA is not decidable. Hence, its complement, the complement of NE sub LBA, which is E sub LBA, is not decidable. Okay. Next, we're going to see a new language called OR sub PDA, which is a set of encodings of PDAs, push-down automata, where this push-down automata accepts all strings except sigma star. And this is not decidable. Again, to show this is undecidable, it's easier to show that the complement is not decidable. So in order to do so, we want to reduce A sub Tm to the complement of O sub PDA. Okay, so we want to construct a reduction that reduces A sub Tm to the complement of O sub PDA. Okay, so we need to construct a reduction. So we're going to do so by computation history, using computation history. Okay, so first we construct a reduction, which is a Turing machine that takes an input of, which is an encoding of a Turing machine M and X. So which is the strings, the input for A sub Tm. Okay, so then it produces a PDA. Okay, so the output is a PDA. We call it P sub M comma X. Now PDA has one stack memory. Okay, so such that M accepts X if and only if P sub M comma X accepts all strings that are not accepting computation paths, that are not accepting computation paths for M comma X. So again, an accepting computation history for M on X is in this, is encoded as this. Okay, so we have a different, we have encoding. So this is initial. And then for the next configuration, we write it in the reverse order, separated by pound sign, and then C3 is the original, and C4 in the reverse order, and so on. Okay, so the last CL could either be CL or CL inverse. So one original, one inverse, one original, one inverse. Okay, so then this is the computation history of M on X. This is encoding. So here is such that, okay. So this is PDA, P sub M comma X, generates all strings that encodes a computation history such that, number one, it does not start with C1. Number two, it does not end with an accepting configuration. Or three, that some CI does not properly yield CI plus one under the transition of M. So this is a really transition function of M. Because we want to say this computation history is not an accepting history, what that means is that so C1 is not a star configuration. So this is, so then of course, so anything that violates accepting computation would be C1 is not a star state, and then some intermediate state configuration that's C1 is not a star configuration, or some intermediate configuration does not follow from the previous one, or the last one is not a substate. Okay, CL is not a substate. Okay, so that's so this P M comma X will generate all such strings. So that's a description of this P sub M comma X. Okay, then P sub M, so to do so, P sub M comma X non-deterministically checks which conditions are met. Okay, so we got 3. So checking 1 is straightforward because X is known. So then checking whether C1 is an initial configuration is easy. And checking 2 can be done by checking that CL does not contain QA. That's also easy. To check 3, M comma X simply guesses I. Okay, so one of the configuration in the middle, and pushes CI into its stack. Okay, and it then compares CI plus 1 now. This is in the reverse order, okay, of CI plus 1. So we can, because it's in reverse order, so we can simply we can pop CI one at a time. Okay, and then to see whether most of them is matches, but there's only one place is a transition tells us it follows it legally. Okay, so so that's the description of this PDA. So because this PDA uses, now this is non-deterministic, and also it uses a stack to check condition 2. It doesn't need stack to check conditions 1 and 3, which can simply be done by which can simply be done by just looking at the input. So this is a finite automaton. Okay, so but checking condition 2 needs a stack memory because you need to remember the previous configuration. In other words, you need to remember 2 configurations. So remember the previous one, and then the next one. In order to do a comparison, it has to be in the reverse order for this comparison to work. Okay, because most of the symbols are the same except on the location of the states, location of the head, and the symbols pointed by the head. So only at that local part, it follows the transition function. Hence, okay, for this description of P sub M comma X, we have M accepts X if and only if P sub M comma S accepts and only accepts non-accepting computation history of M of X. Okay, so which means that P of M comma X doesn't accept everything. So it is not equal to sigma star. Okay. That is, okay, so which means it's in the complement of all sub PDA. Hence, we have this reduction. M comma X belongs to A sub TM. meaning M accepts X if and only if this Turing machine, this PDA does not accept everything. Okay, so which means that it's in the complement of all sub PDA. Hence, all sub PDA is undecidable. So the complement of all sub PDA is not decidable. That means all sub PDA is not decidable. Okay, so that is the end of this video.